right, friends. 3 o'clock. Time for some dynamics. Rawr! Announcements. Not many announcements. Your second exam for the class on Friday. Going to be two topics. Kinetics and working energy. So things that we've covered the last 2 weeks, but not any momentum topics. 2 questions on the test. 1 on working energy, 1 on kinetics. All right. So that's going to be the test. I am making my way through grading your homeworks that you turned in yesterday. I didn't quite finish by the time this lecture started. I mean, there's 50 of you, there's 1 of me, so it just takes a little time. But I'm hoping to get those done by tonight, and I'll post the solutions for homework number 4 after I kind of make my way through all the homeworks. Okay, I'm getting there slowly but surely. So that's that. I've posted practice problems for you to look at, so please take a look at those. And we will do exam review and look at some of those practice problems in class tomorrow. Those solutions for those practice problems also posted. Questions? Looks like I have a question in the chat by Mr. Alex. Our favorite class. Oh, sorry. Yeah, welcome back to your favorite class. Rawr! Okay. We all know it's your favorite class. I don't have to say it anymore. I know that it's true. You know that it's true. Don't fight it. Okay? You know that it's your favorite class. Without further ado, let us pick up where we left off yesterday, and that is talking about conservation of momentum. My favorite topic in your favorite class, your favorite everything. That's how you got to look at it, you know? Always your favorite stuff. That'll make you more excited about it. If you think it's your favorite thing, then you'll make it exciting and do it. All right, so let's get you over the writing pad. Yesterday, we were in the middle of working through an example. And our example was this example. It was the block sort of sliding to the left, and it was going to hit this sort of hitch in the road at point O and begin to kind of curl up. All right, so we want a couple of things. Momentum diagram. Conservation linear momentum in I hat and J hat. We wanted conservation of angular momentum, which will obviously be in K hat. And then we want an expression for angular velocity right after hitting O. Those are the things we're after. We had mostly made our way through this guy yesterday, so I'm going to go through that quickly, and then we'll pick up on these guys. So remember, our momentum diagrams have initial momentum, impulses, final momentum. Our initial momentum. Here's our center of gravity. This box has a mass of m, and it's only moving to the left. So our initial momentum looks something like this, where we have mv1. All right. We have impulses on this particular guy. I guess we should maybe label some of these points, make our life a little easier later. Here's G, the center of gravity. Here is O. Same thing over here. Here's G. Here's O. We have impulses on this guy in the Y direction and the X direction. So here's an impulse of our force at O in the X direction, crazy like a fox. Here's our impulse of this guy, force at O in the Y direction. crazy like a foy. Remember that these are forces that act over a short amount of time. Crazy like a fox, crazy like a foy. And then our final momentum here is point O. And here's point G. And we said that once we struck point O, this box basically has like fixed axis rotation about the corner of the box at point O. So with fixed axis rotation, we have this sort of like radius arm to the center of gravity, which will cause the velocity to generally be in this direction, which is tangent to the circular path that this point will have about the rotation of O. So here, this is MV2. And we also defined this angle as the angle phi and said that phi is the tangent inverse of, because we had dimensions of this box, B and C, we had the tangent inverse here of B on C, obviously, right? And we also have in this particular guy, since we're rotating, we have angular momentum of this box now, which is Instagram omega. IG omega. Instagram omega. All right. So those are all our components of the momentum diagram, including initial, impulse, and final momentum. How are we doing on that? We good? So that was kind of a quick refresher. We had done all of that yesterday, so that is our momentum diagram. Next thing we want to do, conservation of linear momentum in I and J. So let's do that. All right. I hat. All right, remember a general equation for conservation of linear momentum. Well, let's just do the general equation before we get into I hat. General equation is something like the linear momentum at the center of gravity, situation known 1, plus the impulses. So this is F dt equals the linear momentum at the center of gravity, position number 2. And we'll recall that your linear momentum vector is the mass times the velocity. All right, just a refresher. So with that in mind, let's do I hat and J hat. So here is your conservation of linear momentum in I hat, LG1. So we have to look at the linear momentum components in situation number 1. So what we're looking at here is, what are my linear momentum components in this particular diagram? All right, well, in the I hat direction, this particular diagram, we obviously have this linear momentum to the left in I hat. Why does it keep jumping down like that? Stop that. All right, we have the linear momentum of this guy moving to the left. So here this will be negative mv1. Negative m, magnitude of the velocity 1. There we are. Okay, no problem. No problem. Next thing we have to do is consider the impulses that act. All right, well, the impulse that we have here is, wow, I had these backwards. This should be y. Apologies. And this should be crazy like a fox. Got those backwards. Okay, so the impulsive force in the x direction is here. So it acts in the positive direction. Impulse of my force acting at O in the x direction dt. This is all equal to. Now I have to consider my linear momentum component here. So now that we have this sort of like fixed axis rotation, we have a linear momentum that's got components in both I and J. And so we'll have to resolve this linear momentum into the I direction to write it appropriately. And we'll do that through the sine of this angle phi. All right. So here we'll have the mass of the box multiplied by the magnitude of the velocity of the box at the center of gravity in situation number 2. So I'll just draw this as the magnitude V2. We know this is the center of gravity. And this will be sine phi. And since it's kind of moving to the left still, notice it's sort of like points backwards. We're in traditional like XYZ coordinate system. Okay, I guess I should draw that, but I think we all sort of assume that that's the coordinate system that we're in. That we have a negative sign for this component. All right, it's moving backwards in the I direction in the end still. All right, so we're done. This is our expression in the I direction. It's not asking me to solve anything. It's not asking me to rearrange, whatever. It just says write an expression for the conservation of linear momentum. Okay, I did that. Don't do more work than you have to. I'm lazy, I'm old. Similar idea in J hat. No components of linear momentum in J. It's only moving in this X direction. So here initially we have nothing in J. We're going to add to that the integral of the forces at O in the Y direction integrated over time. These are my impulses that act. This is going to be equal to, very similar to this expression here, we've got to resolve our linear momentum into the Y direction, and it's generally positive. So here, M V2 now times cosine of phi, resolving it into that general direction. All right. Bam. Cruising. I've written an expression for my conservation of linear momentum. So here I'm done. Sweet. Let us continue now with what is the newer stuff, and that is conservation of angular momentum. All right. When we do conservation of angular momentum, just like when we do kinetics, we can choose to do our analysis at the center of gravity or at a fixed point. So we can execute at center of gravity. Which for us is the point G. Or we can execute it at a point of fixed axis rotation. Which in this particular problem is point O. So let's have a discussion about these two particular points. You can do the analysis about either point and things will work out perfectly fine, assuming that you do all of the math correctly. Big assumption. So let's take a look at each one of these 2 points and maybe which one will be easier to work through. All right. So here's center of gravity, center of gravity, center of gravity. Here's point O, point O, point O. All right. If I were to do this particular analysis about the center of gravity, I'd have some annoyance when I went to the impulses. Namely that if I did my analysis about point G, I would have to worry about the moments generated by these impulsive forces at O. That's annoying. All right. I don't like that. Not one bit. Right. So because of that, it would be a lot easier if we just did our analysis at point O. Because if we do our analysis at point O, the impulsive forces are passing right through that point, meaning that they're not going to contribute any impulsive moments because there is no moment arm to those forces. All right. So I'll say, because of impulsive forces at O, analysis is easier at O. All right. And that's because no impulsive moments. You could do the analysis about G. Perfectly fine. But it's more annoying. I'm telling you right now. I've done it both ways. That's all I do in my spare time. Practice problems. This isn't the life of Dr. Hart, okay? Easier at O. So let's do conservation of momentum about O. And this is specifically going to be in k hat. So if we're in 2 dimensions, our angular momentum vector will be out of plane in k hat. General equation, the angular momentum about point O, state number 1, plus the impulsive moments about point O integrated over time equals the angular momentum of this object about point O, in situation number 2. And let's recall what our definition of HO is. Just like we recalled the definition of the linear momentum, we'll recall that HO can be both R cross MV or this IG omega. And let's not be specific to any points here. Let's just say that angular momentum is R cross MV or I omega. These are 2 most general expressions for angular momentum. Okay, away we go. Conservation angular momentum. Let's dance. Let's look at our initial angular momentum first, specifically about point O. For that, I'm going to have to go all the way up to my picture here. So again, about point O. All right, so about point O, I will have some initial angular momentum. That's because I have this linear momentum term here that is not acting through point O, but instead I'm going to have a position vector which is locating that guy. So here, this is a position vector which locates G from O. Go figure. And I'm going to end up crossing that with this linear momentum component to get me the angular momentum component. Remember, our general definition for angular momentum is R cross MV, right? So if we're standing at this particular point, then this guy is going to drive some angular momentum for us, which is RGO cross MV1. This is my initial angular momentum of this particular object. I'm going to add to that the impulsive moments. So the impulsive moments here through point O. This force travels right through O, and this force travels right through O. Because they travel right through that point, there is no moment arm to those forces. And so because of that, all of the impulsive moments about O are 0. All right, how are we doing? I don't see any questions. That means everyone understands. Great. Last thing I got to do is my angular momentum about point O in situation number 2. This is where things get a little cray-cray. Here I go. I'm going to use blue here since my figure is getting a little busy. I've got this linear velocity component here. It acts along this particular path, which I know generally to be perpendicular to this vector. Okay? So this guy will also provide for me some angular momentum about this point, and that will be something like RGO cross MV2, right? So here I have some component that is like the position vector arriving at G from O crossed with MV2. But that is not the only angular momentum component that I have. That is the angular momentum that comes from the linear motion of the box. So that is here, this linear motion causing angular momentum about this point. But I also have the angular momentum of the box itself, which is this component here. Okay, so I have to add an additional IG omega. So this is from linear motion of center of gravity. And this is from rotation of box. All right. That's the general idea there. So now let's actually execute these cross products and go through it. Generally, I'd say that if you wrote this, you're done with your conservation of angular momentum expression. So if we go kind of back up to our checklist and we say, what do we need to do with this problem? All right, well, we've done this. We've done this. We have to write conservation of angular momentum in k hat. All right, well, we just did that. Last thing I need to do is an expression for angular velocity right after hitting O. And that will require simplification of this equation here generally. So let's do that right now. Okay. First is this term, RGO cross MV1. So that is the cross product of the position vector that locates the center of gravity with the linear momentum MV1. So I'm crossing this vector here. Why did it do that? With this vector here. Those are the two things I'm crossing with each other. So if I want to do that, understand that we can sort of use shortcuts that we may have seen in previous lives with cross products to see that this is going to be something like, reminder, this dimension here is b on 2. So the cross product between this guy and this guy will be in k hat and have a magnitude of b on 2 times m times magnitude of v1. If that doesn't make sense to you, go back and review cross products. I don't know what to tell you. So this will be b on 2. That's the magnitude of the length of this particular vector to the line of action of this linear momentum, multiplied by the mass of this guy times the initial velocity of this guy, which is magnitude of v1. Okay, baby. Let's continue. Plus 0 equals this guy here. Position vector locating G from O crossed with MV2. All right. Here would be the position vector that locates G from O. The magnitude of this position vector, let's call capital R. Using trig, Pythagorean theorem, you could come up with an expression for R and say that R is what would be the square root of b on 2 squared plus c on 2 squared. That is coming from generally this right triangle here. All right. Could simplify this and write this as 1/2 square root b squared plus c squared. All right, we'll use this a little bit later. Understand that this is the distance between point O and point C in sort of an absolute sense. If that is the case, that simplifies this cross product here a little bit, just because we know the magnitude, we know they're perpendicular to each other. So this will end up being R times M times magnitude of V2. Velocity to the center of gravity in situation number 2. Plus IG omega. IG, you can look this up for a rectangular plate with side dimensions C and B. This is going to be M on 12 times B squared plus C squared. And my omega is going to hang out on the backside. I can cancel some things. M cancel, M cancel, M cancel. Also, we have a kinematic relationship here. which gives us that the magnitude of the velocity in situation number 2 is equal to the value r, which is the distance between O and G, times the angular velocity omega. We've seen this with work and energy. We've seen this with kinetics. Hopefully you're comfortable with this general expression at this point. If not, keep up, dang it. So I'm going to make that substitution here. With that substitution, we're going to end up with something like V times the magnitude of V1 on 2 equal to, making my substitution, R squared omega plus B squared plus C squared on 12 times omega. We can recall that R is this crazy thing by trigonometry. Make that substitution. B magnitude V1 on 2 equals 1/2 B squared plus C squared times omega plus 1/12 B squared plus C squared times omega. Rearrange this guy, solve for omega. We have a now much more simple version of this equation, which is omega is 3 times B times magnitude V1 over 2 B squared plus C squared. That is your final expression for the angular velocity of this block right after it strikes point O, in terms of the initial velocity that it had and the dimensions of the box. Notice, no mass in this equation. Kind of an interesting finding, meaning that the angular velocity of the block, if it like hits this point O, the mass of the block has no bearing on the angular velocity. I think that's kind of interesting. It only really matters how fast the block is traveling and what the general dimensions of the block are. So if it's a block of diamond or a block of paper, they rotate in the same way. It's interesting. All right, how are we doing on that? Questions on that? Okay. No questions? Then I want to move on to another example. And another example that's going to actually use numbers this time, so hopefully that'll help us keep in order. I want to voice over one slide, and then we'll get to that. Voice over like Darth Vader. Do you guys know in the original Star Wars movie, there was like this guy behind the actual Darth Vader mask who talked like this? And it was actually really funny for the actors to think about having him hit with a deep, dark voice much later in the series. Yeah, they actually had to dub James Earl Jones over the Darth Vader guy because he talked like that, which is really kind of funny. Anyway, that's Star Wars for you. I'm a nerd, right? Aren't we all nerds? Yes. So let's talk over this slide. You have multiple objects. The way that we handle multiple objects, if we have to draw like our momentum diagrams and all that sort of stuff, is that we just consider the momentum of each individual object in our equations. So instead of having just a standard equation, we put these summations out front of it, telling us that we add all of the components together of all of each of the individual objects, both for linear momentum and same for angular momentum. So our diagram might look like this if we have a situation that is like this. So the problem might be a bullet striking a plate that initially has no velocity. So the bullet has velocity coming in and it's striking a stationary plate. So initially the bullet is going to strike this object. It itself has some linear momentum. Once it strikes the object, we'll have some impulsive forces here at point C that act. And then the final momentum will have final momentum of both the bullet and the rod. So after the bullet strikes the rod's obviously going to want to have some rotation, and also going to want to have linear motion at its center of gravity. So all these components kind of come into the final momentum of this particular piece. Okay. I actually want to do this example problem with this exact sort of setup, but let's put some numbers to it. So here's this example problem. A bullet weighs 0.08 pounds. That is not the mass, that is the weight. It's fired with a horizontal velocity, 1,800 feet per second, into the lower end of a slender bar, 30 inches in length. If we know that the pin is at a location of h equal 12, so that h variable in the image there is 12, and the bar is initially at rest, let's determine the angular velocity of the bar immediately after the bullet is embedded, and the impulsive reaction at c, assuming that it embeds in the bar in 1 millisecond. Complicated. Give you a second to copy it down if you're working on it, and I'm going to copy the relevant information over here to my writing pad. Maybe I'll throw in some more Star Wars trivia later. Like, did you know that Harrison Ford only signed on to make one movie, and then it was very successful, and George Lucas offered him 2 additional contracts after that, but he was hesitant to sign for 2 more movies? Bet you didn't know that. Different than when he made Indiana Jones, where he knew that he was signing up for 3 movies to begin with. Okay, yeah, trivia. There you go. Never know what you're going to learn with Dr. Hart. You never know. Never know. Okay, relevant information copied. Here we are. We've got this bullet striking this stationary rod. The bullet weighs 0.08 pounds. The rod weighs 15 pounds. The bullet's going to strike this rod at the bottom with a velocity of 1,800 feet per second. The total length of the rod, 30 inches, which if you just want to do this, 2.5 feet, and h is 1 foot. We like to work in feet because our acceleration of gravity is in feet, velocity is in feet. Let's just work in feet, right? Sound like I have like a foot fetish or something. Okay. All right, so let's find the angular velocity after strike. All right, so we need conservation of angular momentum. So let's do our momentum diagram. Can you guys tell I'm like losing my mind here? Not that hard to see. All right, my initial momentum. Here's my rod. And I've got a bullet down here that's just about to strike that particular rod. All right. So here I am pinned at that location C. This guy's coming in. Let's do it in red because red's pretty. This guy's coming in with this linear momentum, which is mass of the bullet, velocity of the bullet, situation number 1. So MBVB1. Subscripts might get a little crazy in this guy, but got to roll with it. Impulses. All right, we've got up here point C. The only impulsive forces that act are the forces from the pin at point C. So we'll draw them in generally a positive sense. So here's the integral of the force at C in the x direction dt. Here is the integral of the force at C in the y direction, dt. Some of you may be tempted to write that there are forces that interact between the bullet and the plate. That is true. There will be force between the bullet and the plate. However, because the bullet sticks to the plate, we can assume that it all sort of moves together in situation number 2. So whatever force interactions we have between the bullet and the plate, we're going to consider that as internal forces between the two. So yes, there's some interaction between the bullet and the plate, and there are forces that are transferred there. But because they're sticking together, they're internal and will no longer be external forces because it's all one system now. So the only impulses that we have in this particular situation is the impulses from that pin, which are external forces. My final momentum. All right, here I am, point C. I'll also have to consider things that are going on at the center of gravity, which is point G. And down here where the bullet sticks in, the problem labels this bottom point here as point B. This will be important because I'm going to use these to label my subscripts in just a second. Obviously, the bullet sticks in to the bottom of this piece now, and it will have a new linear momentum, which is driven by the angular velocity of the rod. So this bullet now has a new linear momentum, which is the mass of the bullet times the velocity of the bullet in situation number 2. All right, this final linear momentum of this bullet. From the bullet striking the rod also now will begin to have some linear velocity at its center of gravity. So the center of gravity of this object will also have something like the mass of the rod, the velocity of the rod in situation number 2. And this rod will also now pick up angular velocity as it begins to spin. And so we can indicate that in this general direction, which here this is Instagram omega. Right. Instagram omega, my new favorite thing. So these are my final angular momentum components. Actually, all my final momentum components. All right, cool. That's that. Now, let's do our conservation of angular momentum. And we can either choose to do it about point G here or about point C. For the same reason as before, I'm going to choose to do my conservation of angular momentum about the pin, which is point C. And that's because these impulsive forces would be annoying if I was trying to determine what the moment those impulsive forces generated were about the center of gravity of the object point G. So I only have 2 points that I can really consider for analysis here. That's point G and that's point C. And the analysis is here about C. So what the hell? Let's do it about C. Conservation of angular momentum. About C. Okay, away we go. Let's do it. C. From C to shining C. All right. Conservation of angular momentum about C. General equation. Angular momentum about C, situation number 1, plus the impulsive moments about point C, integrated over time, equal to the angular momentum, not of G, of C in situation number 2, my final angular momentum. All right. So the angular momentum about C, state number 1. All right. Well, here's C. Here's some linear momentum of the bullet coming in. So there will be some angular momentum about this point C because I have a position vector here, which locates B from C, which here is equal to negative 1.5 j hat feet. Hopefully we sort of understand that. All right. So I do this cross product. RBC cross MB VB1. That's going to be my angular momentum there. So this is position vector locating B from C, crossed with the linear momentum of the bullet, which is MB VB1. All right. That is my angular momentum about point C, state number 1. Plus, impulsive moments. Well, if I'm about C, all of the forces that are impulsive on this object pass through that particular point. There's no moment armed to those forces. So the impulsive moments about C, nothing. Be gone, you 0. Or this is I squared plus 1 squared, if you like. Okay. It's from my triangle meme before class. Angular momentum about C, state number 2. We have a couple of different pieces that we have to worry about here. Okay, so again, here's point C. Now I need to worry about the angular momentum about point C that arises from the linear momentum of the rod about the center of gravity and the linear momentum of the bullet after it's been embedded in the rod at the bottom there. All right, so I'm going to need 3 components, something that includes this, something that includes this, and something that includes this. Those 3 components will be, let's do, I guess, the component of the center of gravity of the rod. So that'll be something like the position vector, which locates the center of gravity from C, crossed with the mass of the rod, velocity of the center of gravity of the rod in situation number 2. That would account for this component located at a distance here, which is the position vector locating G from C away from C. I'm going to add to that Instagram omega here. I've drawn it in the general negative sense, so negative IG omega. Right. By right-hand rule, this has got my thumb into the board. Finally, I'm going to add to this the last component, which will be the component that causes angular momentum from this linear momentum. So I'll need like a, here this is R arriving at B from C. I will need a R arriving at B from C crossed with the mass of the bullet, the velocity of the bullet, state number 2. There we are. That's our conservation of angular momentum expression. Nothing to it, right? I need some kinematics. And we'll note. I can relate in this second situation some things. All right, because I know that point B will be, point C is the center of rotation. So point G will be on a circular path around point C, and point B will also be on a circular path here about point C. That means I have kinematic relationships between the velocity at point B and the angular velocity of the piece, as well as the velocity at the center of gravity and the angular velocity of the piece. So note that the velocity of the center of gravity, situation number 2, magnitude, is the distance that that guy is away. So I'm talking about this general velocity here is located this distance away. All right, so that distance there is 3 inches from the problem. So here this is 3 divided by 12 feet multiplied by the angular velocity of the piece. Okay, this is like V equals R omega. So the velocity of the center of gravity of the rod in situation number 2 is R, which is 3 inches, 3 on 12 feet, times omega, the angular velocity of the piece. We can do the same sort of thing for the bullet, because the bullet down here is stuck into the plate, but that guy is 18 over 12 inches away, or 1.5 feet away. Okay, also, the velocity of the bullet in situation number 2, here the magnitude, is equal to the distance that it is away from that center of rotation, 18 on 12 feet, multiplied by omega. This is relating these linear velocities to angular velocities. Goes back to fixed axis rotation, goes back to stuff we talk about in week number 1, week number 2. Told you that stuff wasn't going away. I told you. All right. So with that in mind, we can make substitutions like up here. I can make substitution here, so on and so forth. Because I'm looking ultimately for this angular velocity in state number 2. Well, let's go. Rawr. This guy first. Position vector locating B from C crossed with the linear velocity of the bullet. All right, well, I'm going to start putting numbers in here. We have, it's going to be negative. If I do this particular cross product here, this guy cross this, my thumb's going to be into the page of the board. So it'll end up being a negative k hat. That distance is 1.5 feet multiplied by the mass of the bullet, 0.08 pounds, divided by the acceleration from gravity, 32.2 feet per second squared, multiplied by the velocity of the bullet initially, 1,800 feet per second. All right, so that is this cross product term. Plus 0 is going to get me equal to, now I'll take a look at this term. All right. The position vector locating G from C, well, I know that's 3 inches, crossed with the mass of the rod multiplied by the velocity of the rod. Okay, I'm going to make that substitution here. So here, this will again be negative in direction, 3 on 12 feet. This is the distance from G to C. 3 on 12 feet multiplied by the mass of the rod, which we're told in the problem is 15 pounds, divided by 32.2 feet per second squared, multiplied by the velocity at the center of gravity of the rod. All right, well, I have that here. All right, so the velocity at the center of gravity of the rod, this is 3 on 12 times omega. All right. Continuing, I have this term here. This is the angular momentum of the rod. I'm going to subtract here because it's generally drawn in the negative direction. Mass moment of inertia of the rod is 1/12. The mass of the rod, which is 15 pounds, divided by 32.2 feet per second squared, multiplied by the length of the rod, which we know is 2.5 feet squared. All right, so this is like the IG term, 1/12 ml squared times omega. So that takes care of this term here. And then my final term, this is coming from the angular momentum that this bullet causes. I'm going to add to this a negative because the cross product is negative. The distance from the fixed axis point to where the bullet is hitting, that is 18 inches divided by 12 to get me in feet, times the mass of the bullet. Remember, mass is the weight divided by acceleration from gravity, which is not 9.81 in this situation. And I'm going to multiply this by the velocity of the bullet, which has this kinematic relationship with the angular velocity, which is 18/12 times omega. Whew, my head hurts. I got a question. What's my favorite scary movie? I already told you, it's Titanic. Oh no, not a foot fetish. Oh geez. I already told you, my favorite movie is Titanic. They sink in the end. I'll make a long story short here. Omega is the only unknown. Can solve. You'll have an angular velocity here, which is going to be 24.3 radians per second. Yikes. Complicated. Lots of stuff going on. Cross products and, conservation of angular momentum. You got mass moments of inertia, angular velocity, kinematic relationships. Pummeled. All right. We'll finish up this problem tomorrow, and then we'll dive in on review for working energy and kinetics. That'll be it for today. Thanks for coming. I hope you stayed awake with my terrible jokes. You are going slowly mad. Thank you. I appreciate that, Jess. That's nice. It must be the Star Wars trivia. You must really like that Star Wars trivia. Or the fact that Titanic is my scariest movie. Leo dies in the end. Spoilers. How did he not win an Oscar for that? Well, that's obvious. He didn't win an Oscar for that. He didn't win an Oscar for Catch Me If You Can. He didn't win an Oscar for Man in the Iron Man. Oh, wait. He didn't win an Oscar for He Slept in a Bear. Revenant? I know. What the hell? I don't even remember what else he was in that he didn't win an Oscar for that he should have. Sleepless in Seattle? No, that was Tom Hanks. Once Upon a Time in Hollywood? Yeah, obviously. Frankly ridiculous. Big Tarantino fan. Kill Bill, pretty solid. Reservoir Dogs, solid. That was one of Tarantino's first movies. Yeah, Pulp Fiction. Not everybody knows Pulp Fiction. That's a great movie. Pulp Fiction, great. Reservoir Dogs, man, that movie is great. If you haven't seen Reservoir Dogs, got to see Reservoir Dogs.